So, last class we have discussed the problem formulation of quadratic optimization problem using the simplex method. If you recall, we have this is the quadratic function. Our problem is to minimize f of x, which is in quadratic form, and we have a inequality constant and equality constants. But this inequality constant and inequality constant, they are affine functions, linear functions. So, we have formulated this thing into standard Lagrangian function. Inequality constant we have converted into a equality constant, then it is what is called Lagrangian function is formed. Then mu lambda is a your Lagrange multiplier, which is associated with the equality constant, and that equality constant that lambda associated with the equality constant, and the lambda value is not restricted, that its value can be positive and negative and 0, whereas this factor is associated with the inequality constants, and this Lagrangian multiplier corresponding to inequality constant we consider as a mu, that is greater than equal to 0 when this type of inequality constant we have. That is we have discussed earlier in details, that why the mu value should be greater than equal to 0. So, if you now write the what is called KKT necessary condition, we have shown that these are the equation we will get it, equation number 2, 3, 4 and 5. So, this equation we can write into matrix and vector form, which will be equal to into this form, that first is x variable, then we have considered mu Lagrangian multiplier associated with the inequality constant, then Lagrangian multiplier equal to what is called that next is variable we have considered the s associated with the, that is your select variables, then we have considered lambda, these two are lambda. Lambda is since unsigned, we have split up into two positive quantities. So, this equation number 2, 3, 4 and 5, if you write in matrix form equation number 2, 3, 4, if you write in equation number matrix and vector form, it will come into this structure B, this whole matrix I am writing B into x, x is the all variables Lagrangian multipliers and the your decision variables, and right hand side is the D we have defined is D. So, we have to solve this one. Now, this problem is simply a what is called algebraic equation B x is equal to D. So, this problem we cannot solve directly, what we consider we introduce what is called a artificial variable along with this one B x is equal to D, we have considered artificial variable B P, and P how many vector, this is a vector of dimension n cross m plus P into 1. So, there are m plus n plus m plus P variables are there. So, this artificial variable all elements of each artificial variables, which is a P is a vector, we add together, and that W is called artificial cost function. So, look at this expression. So, our problem is minimize this artificial objective function subject to the constraints. What is the constraints we have? We have constraints these equations, which is converted into a standard LP problem, is a standard LP problem. Our problem is minimize this artificial objective function subject to this objective function. Now, we know this B matrix. If you now I write in tabular form to solve in the simplest method, you can see carefully that how I am formed these matrices. So, the equation number 2, we have taken a simple example we have seen where H, N, C, A, B, E and all these things are C, all these things are described in the examples. So, I am just writing the equation number 2, this equation number 2, this one, which in turn it will come this and this equation. So, now this is our one equation number 2, this is we got from equation number 3, and this is we got from equation number 4. With each equation there is an artificial variable p. With this equation p 1 is there, with this equation p 2 is there, with this equation p 3 is there, with this equation p 4 is there. If you write in tabular form now, it will be like this. See, x 1, x 2 our the two original decision variable, then x 3 is corresponding to our mu, then x 4 is corresponding to our artificial variables. Agree? Then x 5 is corresponding to y, and x 6 corresponding to z, and y and z combinedly they formed is a Lagrange multiplier associated with the equality constants. So, remaining x 7, x 8, x 9, x 10 are the what is called artificial variable introduced in the system equation, that is b x plus p, this one. So, this s is our slack variables. Agree? I mentioned earlier artificial is a slack variables x 4. So, now how is formed this table? You see 2 x 1, coefficient of x 1 is 2, I have written 2. Then you see there is no coefficient of x 2, that x 2 is 0. Then there is a, this is we have denoted is x 7, what is called that y is we have denoted in x 5. So, x 5 coefficient is 1. So, x 5 coefficient is 1. Then z is x 6, we have defined x 6, that coefficient is minus 1, I have written minus 1. Then mu is the that variable is defined at x 3, that coefficient is 1, say x 3 is 1, and remaining coefficient is 0 except the what is called artificial variable. There is a artificial variable p 1, you can see from this expression that p 1. So, we have written this attribute x 7 is 1 and is equal to 6, that is the first equation we have written, and similarly second equation you can write it, which you will get it this equation, and their artificial variable is x 8, coefficient is x 8 is 1, and from equation 3 you see x 1 plus x 2 plus x s is defined by a variable x 4. So, it will be x 1 coefficient 1, x 2 coefficient 1, x 4 coefficient 1. See x 1 coefficient 1, x 2 coefficient 1, x 4 coefficient 1, and this is a third equation. Then p 3 will come, and p 3 coefficient is p 3 corresponding to x 9 is 1, and this equal to 4, that 4. Similarly, last equation one can write it is nothing but x 1 minus 3 x 2 plus a artificial variable, that will p 4, which is we define a new variable x 10. So, it will be you see this 1, then minus 3, and then 10th position is equal to 1. So, this now how you get that artificial variables, that is the artificial variable. Now, what is the artificial cost function? That is we have written sum of p 1 p 2 up to p n, in our case up to p 4. So, if you just p 1 p 2 p 3 p 4, and what is p 1? P 1 from this equation p 1 is nothing but a 6 minus, if you take that side right hand side, 2 x 1 minus x 3 minus x 5 plus x 6, agree, is equal to x 7, and x 7 is nothing but a p 1. Similarly, p 2 is equal to x 8 is equal to p 2, I can write is 6 minus 2 x 2 minus x 3 plus 3 x 5 minus 3 x 6, if you take that side, is equal to p 2. So, if you similarly I can write p 3 and p 4. If you add all these things, I will get this one. So, the artificial objective function I can write it now 4 x 1 minus 4, then 0, there is no x 2, x 3 minus 2, x 4 coefficient minus 1, x 5 coefficient 2, x 6 coefficient minus 2 is equal to, that is we have denoted w. So, w we have written. So, now we have to follow our standard simplex technique to minimize this objective artificial objective function w equal to 0. That is how we are. So, next step is what? You find out the pivot column. This you just look the what is the maximum negative coefficient associated in the artificial objective function here. So, this column is the pivot column, and what is the pivot row? You divide this coefficient along this column, the 2 divided by 6 divided by 2 is this is 3. You can write it, this is 3, then this is 0, ignored, this is 4, 4 divided by 1, that 1 divided by 1, this is 1. So, this is the minimum ratio, you got it. So, this is our pivot element and this is our pivot row. So, this way we have identified pivot row. Then after that you know that x 1 will be entering as a basic variable and x 10 will live as a non basic variables, and then procedure whatever we have discussed earlier repeat for few iterations, then you will get the final solution of this problem. That means, the initially problem is given, if you see the initially problem is given a quadratic optimization problems to solve that by using what is called simplex method. That is, this quadratic objective function is quadratic, and what is our our inequality constant and equality constant and affine functions this. So, this is called quadratic optimization problem that can be solved by using what is called simplex method. Before that you have to convert what is called KKT necessary condition by converting into Lagrangian functions. So, this is we have discussed last class up to this. So, please solve this problem, complete this problem. You will see after few iteration the solution is given x, after 4 iterations see what is the value of x 1 is coming, this is 13 by 4, x 2 is coming 3 by 4, then x 3 is coming 3 by 4 that way. So, our basic importance variables are x 1 and x 2. So, this solution you will get optimum value of the function at x 1 when it is 13 by 4 and x 2 3 by 4. So, today we will start, that is the solution of what is called optimization problem using interior point method. So, our next topic is interior point method. Interior point method for solving optimization problems. So, interior point method can be used for solving the linear programming problem. First, it can be interior point method can be used for linear standard linear programming problem, linear standard programming problems, and also we can solve the convex optimization problems, convex optimization problems. That includes inequality and equality constant, that includes equality and inequality constant. So, you through interior point method we can solve two class of problems. One is linear problems, linear standard LP problem, another is convex optimization problems along with the inequality and equality constant. Standard LP problem may be equality and inequality constants also there in relation to this. So, let us see that what is our standard LP problem. Standard LP problem recall our standard LP problem is minimization, f of x whose dimension n decision variable is we return C transpose of x n subject to this standard LP problem I am writing. If you can recollect this thing, that what we have discussed earlier, A x is equal to B dimension is n, m cross n, this agree, and B is greater than equal to 0 and x is greater than equal to 0. And we define now feasible region. We have to find out the solution of this problem such that the function value is minimum, not only minimum, it must satisfy this equation. That means that point at which the function value will be minimum, that point must be inside the feasible region. Then what is feasible region? The feasible region, as we define like this way, define the feasible region f is the feasible region. Let us call this is the feasible region, that f we had denoted, this is the feasible region, feasible region f is denoted by x, any point in this feasible x, it must satisfy all equality condition of standard LP problem, that is standard A x is equal to B, it must satisfy for x greater than equal to 0. So, this if for any value of x in this region, if it is satisfy this one, then f is called that feasible region of the corresponding problem. So, simply definition is like this way, x whose dimension in n cross n is called an interior point of f. F is what? Feasible region. X is called interior point of f. This means if any point in the feasible, any point inside the feasible region is there, if consider that point is the interior point of f. If x superscript this belongs to f, and not only this, every component of x must be greater than equal to 0, and also x j superscript 0 means any point on the initial point is must be greater than equal to 0 for j is equal to 1 to dot dot n. So, this is the definition of interior point. So, if you have a feasible region, if the point is belongs to this in the feasible region and it satisfied that the all values of x is greater than equal to 0, then this point is called interior point of the feasible region. Agree? So, let us see that how one can solve this type of problems, whether it is a linear programming problem or it is a convex optimization problem. What are the basic steps are there to solve this problem? So, our algorithmic steps are like this way. So, what is the algorithmic steps? First, you find out the interior point, agree, of the feasible region of the problem. Then you move from this point in such a direction, so that the function value, the objective function value decreases. Agree? That objective function value is decreases. That means we are in the interior point. From there we move in such a direction, so that function value is decreases, and then test it whether this point has reached to the optimal value of the function or not. If it does not reach to the optimal value of the function, then move to another point, okay, so that the function value is decreases from the previous value of the function, and in this way we can reach to the optimum value of the function. Starting from the initial starting point should be inside the what is called interior point. So, our algorithm steps first step is find an initial feasible point solution. Okay, to begin the iteration process. This is first step, and next step, step 2, generate a new point. Next is generate a a new feasible interior point that will give lower objective function value. That means, from the initial point you move in such a direction, so that function value is decreased. Step 3, test it for optimality. Test the new point for optimality. If it is not optimal, if it is not optimal, move to the, if it is not optimal, repeat step 2 until optimality is reached. So, this is the 3 basic steps where we will adopt for interior point methods. So, let us see that how to find out the what is called the feasible direction. So, next is definition. A direction D whose dimension is same as the feasible decision variables, a direction D whose dimension n cross n is a descent direction if moving along the direction decreases the function values, function value of the objective function. That we have discussed in details when we have discussed the how to find out the optimum value of the function by using steepest descent method, if you recollect our earlier discussion. So, let us see this one. Suppose we are in the feasible region, interior point of the feasible region, and we are here. Let us call first, that is x superscript 0, we are here, and we move in such a direction, so that the function value, objective function value is decreases from the previous value of the function. So, let us call this is our direction. that if we move in this direction, then this function value will decrease. So, parallel to this one, we are here now parallel to this one. So, this one parallel to this one. I moved in this way from this state I moved like this way. So, this is our, we can say it is a lambda into d, where lambda is greater than equal to 0, greater than equal to 0. If it is 0, then this is this point. So, now where is our new vector of x? This is our new vector, and that is our x. So, we moved from initial vector which is in the feasible region in such a direction, so that the new vector, new decision variable, with the help of new decision variable, the function value should decrease. Okay, that is our basic. So, this is our x 1. Let us call for 2 dimensional case, 2 decision variable case that can be extended for n dimensional decision variables. Okay. Note now, see this one, our objective function value is what? Objective function value, objective function f x is equal to C transpose of x, and let d is the our descent direction, that d is the descent direction. And in this direction, if you move from this initial position, if you move in this direction, agree, and if we are here, then our vector is x is here. So, we can write it C transpose x must be equal to C transpose of our initial vector, initial decision values of this vector x. This must be the word. Then we are moving in the right direction to minimize the functions. So, that is the direction, what is called descent direction, and from this point we parallel to this one we drawn this one. Now, we can write it C transpose x is what? This vector plus this vector. So, x of superscript x of 0 plus lambda into d, and d is a vector of dimension n cross 1 is equal to less than C transpose x of 0, and then C transpose x of 0 plus lambda is a scalar quantity, we can take it out and we can write C d is equal to C transpose x 0. So, this cancelled. Since lambda is greater than 0, greater than equal to 0, so you can write that C transpose d is equal to 0. That also we have discussed in earlier in steepest descent method. Now, what is your conclusion? Which direction we will move? If you can move in this direction and this direction, how will you decide? If you decide d is equal to minus c, then from equation 1, that means this condition indicates that our function value will decrease if we move from x to x 0 to in this direction, agree, and this will be function value will decrease, and this condition must satisfied, and when this condition must satisfy this one, sorry, this is greater than equal to, less than equal to, when this condition will be satisfied, if one of the choice of d is, if we consider d is equal to minus c, then from equation 1 we can write it from 1, we can write it C transpose into d is minus c is equal to, let us see what, that is minus C transpose c. This is nothing but a Euclidean norm of that C vector and square, and this quantity, if you see this quantity always greater than 0, greater than equal to 0. Okay. So, this indicates this quantity, since it is minus sign is there preceded with minus sign, this is preceded with minus sign, that whole quantity is less than 0, this quantity. So, this you can write it less than equal to 0. So, this is the condition that one of the choice of descent direction is will be with minus sign of the cost function coefficients. So, now we have and if this is the direction and this x is belongs to this feasible region, if we move in this direction and that final vector is x, if it is belongs to what is then feasible region, this new point, this is the new point, it must satisfy our equality constraint. If you see, this must satisfy our equality constraint, agree, is equal to b. Let us see what is this one. X is what? X 0 plus lambda d is equal to b, and this x 0 plus lambda into a d is equal to b, and this quantity, since x 0 is belongs to the feasible region, means interior point of the feasible region, this quantity is b. So, therefore, this condition is a into d is equal to 0, since lambda is greater than equal to 0. Lambda, since when you are moving from this point to some point, then lambda quantity is positive, you can omit 0 also if you like. So, this is the condition. So, so a and d must be 0, this is the conditions, we got it. So, remarks, what is the remarks, we can write it for this one. If d is the descent direction, okay, is a feasible direction, it must satisfy a d is equal to 0. If d is a feasible direction, that it must satisfy. Feasible direction means what? Feasible descent direction, you can write it, feasible descent direction means that the function value will decrease if we move in these directions, and it must satisfy our equality constraints also, okay. So, satisfy this one, and not only this, the x which is equal to x 0 plus lambda d must be greater than 0 to satisfy the non-negativity of the decision variables. This is a non-negativity restrictions on the decision variables. In short, if d is the descent direction, then it must satisfy a into d is equal to 0. This is the what is called equality constraint must satisfy. Let us take one simple point and see the effect of interior point, then how to choose the interior point of this one. Example, this is we have given till now some basic definition of this one. Let us call minimize f of x is equal to minus x 1 plus x 2, agree, which you can write C transpose minus 1 1 x 1 x 2, which is nothing but a C transpose x dimension 2 cross 1, subject to x 1 plus x 2 is greater than less than equal to 5, then x 2 is less than equal to 4, and x 1 and x 2 is greater than equal to 0. This is our problems of this one. Now, let us see if we represent this one in graphically what it looks like. This is easy to represent. First we have a coordinate axis x1 and this is x2, and this, since x1 is greater than equal to 0, then this indicates the upper half of this from this line. Since x2 x1 is greater than equal to 0, this means this part of this one will be our feasible region. Okay. And another constant is that x2 is less than 4, that x2, suppose this is 4, this is 2, 2, 4. So, that should be less than equal to this. So, this. Now, we have a x1 plus x2 is less than equal to 5. So, when x1 is 0, x2 is equal to 5. Let us call this is the 5, some 5.5. And similarly, when x2 is 0, x1 is 5. So, let us call this is 2, 4, 2, 4, this is 5. So, you draw this, you draw this line, okay, and this region, below this region is the feasible region. So, our effective feasible region is this portion. This from here, this is the feasible region. Let us take, there are 2 points are there inside the feasible region. Interior point, we take 2 points. Let us call one is let us call, we take the 1.5 and 1.5. This coordinate is, let us call 1.5 and 1.5. Sorry, it is here somewhere, not here. This point, this is 1.5. Let us call this coordinate is 1.5 and this coordinate is 1.5 here. Then another coordinate you consider, that 3, 1. Let us call this is a 2, this is a 3 and 1, this is 2, our case the 1 will be somewhere here. So, this coordinate is 3, 1. So, this point we will call the point B and this point we will call the point A, this point. Okay. So, there are 2 points are there, we have considered inside the interior region, the interior point. Now, we can say that point A is more centered, point A is more centered than the point B. We can say point A is more centered than the point B, and point B coordinates are 3, 1 and point A coordinates are 1.5 and 1.5. More centered in the means this point A point is equidistant from the coordinate axis. This is 1.5, from here also 1.5 equidistant, and this here off centered. You can say this point B is more off centered compared to A. So, now clearly if you see our objective function is what? If you see our objective function is this one, this function we have to minimize. Agree? When f(x) this equal to 0, means objective function value is 0, we can write x1 is x2 is equal to x1. That means, our objective function expression is that one with a 45, slope is 45, and this is our objective function value f(x), which is given minus x1 plus x2 is equal to 0, this one, and it is passing through the origin. Now, you see this objective function line, if you move in this side, the function value is decreasing, 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 and at most you can go at this point when it is crossing this one. At this way, its function value is minimum. Okay. This is graphically one can see that one. So, if you move in this direction, the function value is increasing, and from this one, if function value is decreasing. Now, if this point A is the our, you can say, starting point of our iteration of interior point this, then which directions we have to move it? Just now we have proved it, the choice of D must be equal to choice of D, what is called direction vector will be minus C. And what is C? Just say C is, our case is minus 1 and 1 is C. So, with minus sign, I have keeping with multiplied by with minus sign 1, whatever the vector you will get, in that direction you move it. Let us call C is what? That C the what is called our objective function. This is the C transpose is minus 1 plus 1. So, take that C is minus 1 plus 1 this. Agree? So, our C is minus 1 in these directions and plus 1, it is a 2 plus 1 somewhere here. So, this. So, this is our C vector. Agree? So, our D vector will be which one? If you see our D vector is opposite to this one. So, this is our D. Agree? So, which direction from this point, which direction? Parallel to this direction you have to move it. Parallel to this direction, from this point A I have to move parallel to these directions, and this direction is in these directions. So, this, if you move in this direction, the function value is decreased, and physically also or graphically also you can see, if you just move in this direction, you will get optimum value of the function at this point. Let us call this point is C, you will get it this, and here if from A point you have to move in this direction. Let us call, if you are at B point, you have to move from this point parallel to the D in these directions. Okay. So, this point and difference between this point and this point, if you move in this direction, it will hit the wall at some iterations. Okay. So, you can say this one, that is, if both the cases function value is decreasing, no doubt. So, we can make a remarks like this way. It is clear that f x function value decreases more, decreases substantially by moving along the steepest descent direction. From point A. On the other hand, point B, the off center point B is the off center point, will take us towards the wall, agree, of the feasible region, before much improvement can be made. So, now question is how to center, because our initial guess may be anywhere in the feasible region. Now, question is how to center the off center point in a feasible region. The simplest way is do some transformation on the original decision variables, and that will transfer the original point into a what is called transform point, which will be the center point. Center point means from the axis, the distances will be same. So, next our point is how to center an interior point. Suppose in this case, suppose we are at this point. Now, this point how to make it centered? So, you have to do the initial variables x 1 x 2 some transformation which will convert into new variable. In new variable we will get the center point from the x from center point from the both axes. The point will be in the transform axis, the point will be equidistant from the coordinate axes, transform systems. So, let us call we take one example and explain what is the meaning of this one. So, let us call we consider our point B point which is off centered. The point B is off centered point. Suppose this we take it. So, if we take it, now we do transformation like this way. After that transformation, you will get new coordinate axis and that point should be equidistant from the coordinate transform coordinate axis. So, we define new coordinate axis y 1 is equal to the old value of x 1 divided by 3, then the coordinate y 2 is a x 2 divided by 1. Now, you see whatever this coordinate is, I got it, the x 1 of 0, x 1 of 0 divided by 3, x 2 of 0 divided by 1, this what we will do. So, it is better to write x superscript 0, 0 then 0. This is the transformation we made initial point which transforms, since it is the off center point, that point is not a equidistant from the axes. One is 3, x axis is distant from y axis, the distance is 3, from y axis from the x axis distance is 1. So, it is a off center point. So, we have made it this one, which equivalently we can write into matrix form y 0, y 1 of 0, y 2 of 0, this equal to, write it, that one is what we get 1 by 3, that is 1 0 0 multiplied by x 1 0 x 2 0. Okay. Now, you see if you substitute, this is the transformation. So, what is this is coming, if you do the x of 0, x 1 of 0 value is what 3, the x 2 of 0 value is 1, then if you this into this value is 1 and this is 1. So, now see this one, the transform coordinate axis, the point y 0 point is equidistant from the transform coordinate axes 1 1 is. So, now see our in transform system what is our what is called our optimization problem, we will see. Now, substituting the values of x and x 0 agree in terms of y 0 by substituting, minimize the function which will be in terms of y is equal to minus x 1 plus x 2. X 1 is what? Just say x 1 is 3, x 1 is 3 y 1, 3 y 1. Okay. In general, now if I write it in general, this is the 3 y 1, then x 2 value is y 2. So, this which you can write it, this is minus the 3 1, this is minus 3 1. So, I can write minus 3 1 y 1 y 2 and corresponding to this value, this point x 0, that is it will be 3 y 1 0 y 2 0. Agree? In general, this is the transformation we made it this one. Then subject to our is x 1 plus x 2 is less than equal to 5, which we can write it x 1 is what? See this one relationship between this, x 1 is 3 x 2. In general that relation is what? Y 1 is equal to x 1 by 3, and that corresponding point we can write it this one. Agree? So, this is that one, and we can write 3 y 1 plus y 2 is less than equal to 5. So, now it is converted, this is in transform coordinate axis. Our problem in minimization f of y, what is f of minus 3 y 1 plus y 2, and subject to this condition. Another constraint is there, what is called x 2 less than equal to 4, which equal to nothing but a y 2 is less than equal to 4, and then y 1 and y 2 is greater than equal to 0. So, if you transform coordinate axis, we can say minimize f of y, what is objective? Minus 3 y 1 plus y 2 subject to constraint, inequality constraint 3 y 1 plus y 2 is less than equal to 5. Another inequality constraint is y 2 is equal to less than equal to 4, and y 1 y 2 are greater than 0. Since why it is greater than 0? Since x 1 is x 1 and x 2 greater than equal to 0, x 1 x 2 greater than equal to 0, that is why y 1 y 2 is greater than. So, now you see, if you just redraw this optimization problem in what is called graphically, if you plot the optimization problem, this looks like this, and you will see that point in coordinate new coordinate system, that point is in the center point. So, I am now plotting that one. You see this constraint, this is the one constraint, this is another constraint 2, and this constraint. So, our new variables in transform variables are y 1, y 2, and y 1 greater than equal to 0, that means it indicates it is this side, and y 2 is greater than equal to 0, this indicates this is that side. And we have another constraint in transform coordinate axis, y 2 is less than equal to 4. Suppose this is 4, 1 2 3 4, suppose this is 4, this is 2. So, this is one thing is that one, and our inequality constraint you see this one 3 y 1 plus y 2 is equal to 5. Let us call y 1 is 0, y 2 is 5, y 2 is 5 here. Then y 2 is 0, then y 1 is 5 by 3, that means 1.66. So, this is 1, 1, 2, then it is a 4, this is 1, 1.6 maybe here. So, our that constraint is that one. So, this, so our feasible region is that this shaded blue shaded portion, this is the polynomial, and our what is our initial interior point 1 1. So, this is 1 and that is 1. So, this is our initial point in transform journey, initial point, that is 1 1, which is a centered point, this is a centered point. Okay. So, in general now we will show how to convert, if it is, if the point is off center point, how to convert into a center point in transform coordinate axis, that we will discuss next class in details, this one how to convert into that portion. Okay. So, we will stop it here now.